Does work? All right, sounds good. Welcome to the Richard M. Karp lecture for today. My name is Sandy Arani, and I am the Associate Director for the Institute. All of you are probably pretty familiar with it, but I have a standard shtick about the Simons Institute, founded in 2012 with a generous grant from the Simons Foundation. We are the world's leading venue for collaborative research in theoretical computer science. Before we get started, just want to go through some logistics. It's going to be a hybrid talk. So if you're in the room, feel free to raise your hand and ask a question. The mic will pick up your question. I'll be monitoring on Zoom for questions, and let me know if you want them in real time or at the end or as we go is okay. So the Richard M. Karp Distinguished Lecture Series was founded to celebrate the contributions of the Simons Institute founding director, Richard Karp, and his many contributions to the field of theoretical computer science. It features distinguished scientists in the field related to the program and is geared at a general scientific audience and is made possible by many contributions from members of our community. We're very happy today to welcome Eric Allender to be our Richard M. Karp speaker for the day. So Eric has been well known for many years as a leader in computational complexity. His work sort of sits at the intersection between complexity and Kolmogorov complexity, studying how random objects are. He received his BA from University of Iowa in 1979 in CS and theater. So we should expect a really dramatic talk today as a result. He got his PhD from Georgia Tech in 1985, and since then he's been at Rutgers, rising up through the ranks, now a distinguished professor, serving a stint as department chair. He's had numerous leadership roles in the theory community and SIGACT and the Computational Complexity Foundation. And during the 2009-2010 academic year, he's a Fulbright Fellow in South Africa. So his talk today is titled, How Complex is Complexity? We don't have the tagline for it there anymore, but what is it? There it is. All right. So please join me in welcoming Eric. Thanks.
So this distinguished lecture series is supposed to be for a more general audience. So you won't learn anything, but this is going out to everybody in internet land, and they might want to know what all this meta complexity is, and that's what this title is, what's a meta for? So as a goal for today, I want to just give a high-level overview about what this program, this semester is. And since I'm just a few miles from Silicon Valley, I guess I need to mention that this meta has nothing to do with any other meta that you might have heard about. Why are we having this program? I'm going to try to explain some of the reasons for excitement and optimism in the field and illustrate some of the topics involved via examples and, yes, metaphors. And the other goal I have is I really should apologize for that terrible pun. Actually, my respect for humanity went down a couple of notches when I did an internet search and I found that I'm not the first one to reach this low for that metaphor pun. But nobody stopped me when I said that there's optimism in the field. Really? I mean, complexity theoreticians are not known for being a particularly optimistic group. We've had that ground out of us over the last few decades. And so in order to present some historical perspective about that, let's go back to our origins. In the beginning, Hartmanis and Stearns created complexity theory. And sure, they got the Turing Award later for that, but at the time, the critical reaction was decidedly mixed. And what's the reason for this? Well, sure, they were able to show that there were some problems that were hard to compute, but the only things they could say anything about were these really artificial problems, things that nobody really wanted to compute anyway. And so this white noise is to illustrate the universe of natural computational problems at the time of Hartmanis and Stearns. And the point is that yes, complexity theory was created, but this universe was still without form and void. And then Cook and Karp said, let there be light. They provided an organizing principle, and more precisely, Cook provided it, but people didn't necessarily get the message until Karp said it much more forcefully slightly later. And of course, Levin also was saying the same thing about the same time, but nobody heard that in this hemisphere. But what did they provide? They gave us this fantastic tool of efficient reductions, this organizing principle. And what happened is that things coalesced into these meaningful units, these equivalence classes, things that were basically different manifestations of the same problem. And amazingly, they corresponded to natural complexity classes. And when you refined the notion of reducibility, you got more and more classes of problems that are complete for more and more complexity classes. And honestly, I think the message still hasn't gotten out to the wider community to the extent that I think it should have, just how amazingly successful this has been at making sense of this universe of computational problems. When there are a few outliers that still haven't been shown to be complete for anything that we would call a complexity class. But honestly, if you look at the thousands and thousands of problems that people have considered, the overwhelming majority of them turn out to be complete for just a handful, a few dozen complexity classes. I mean, a few dozen doesn't fit on the slide, but it's still a pretty small number. So what else was happening at about the same time? The first positive application of complexity theory arose, namely cryptography. I mean, knowing that something was hard to compute used to be a bad thing, but now, what else is it? It's great because it gives us the ability to do something really useful. So here we are, the early 70s, and we've got a way to make sense of what had just been a perceived difference in computational complexity of different problems. But now there was a framework to support these intuitions. And on top of that, there was a way to make it useful in practice in the form of cryptography. So all that needed to be done was to show that this framework was real in order to enter into this paradise. And then we got a gut punch. Thou shalt not enter into this paradise by means of any tool at thy disposal. I mean, this was actually a three-headed oracle, Baker, Gill, and Solovey. And the paradise that they're talking about is this paradise where we actually know something about the complexity of problems instead of just being conjecture. And of course, they said it much more clearly than this nonsense I wrote there. Namely, they gave us an oracle relative to which P is equal to NP, another relative to which P is not equal to NP. And the lesson was that this meager toolkit of mathematical techniques that we had were going to be pretty much useless in attacking the big problem. And here at the left side, you see a group of complexity theoreticians hanging their heads in despair because they don't know what to do next. But some people did have a clever idea what to do next. It didn't really seem to make sense to talk about attaching oracles to really small complexity classes. And so there was some great work done on really small circuit complexity classes. AC0, the class of things doable with constant depth circuits of AND and OR gates. In the early 80s, we saw great sequence of lower bounds by first Sachs and Sipser, Oita, Yao, and Hostad, and followed very quickly thereafter by lower bounds for a richer class of circuits, the same class of AC0 circuits, but augmented by modular counting gates as long as they were counting modulo a prime by Razborov and Smolensky. And that was followed very quickly by not much. This really petered out, and a quarter of a century later, Ryan Williams proved this really amazingly beautiful result that's amazing to those of us who know just how hard it was to get here. But explaining it to this larger audience, it looks ridiculous, right? I mean, we've gone from prime P to mod 6. We proved a little bit more than that, but I don't want to give the definition. And here we were talking about lower bounds for really easy problems. Here we're talking about non-deterministic exponential time. And we had to overcome a lot of barriers just to get that far. So what else happened in this time? Well, significantly, in spite of these oracle results, this theory of interactive proofs was developed, which was later realized gave us non-relativizing proof techniques. There are oracles. So IP, interactive proofs, was this generalization of the normal notion of proofs that people had been working with. And the initial intuition was, yeah, it's probably pretty close to NP. And there are oracles relative to which co-NP does not lie inside IP. And then there were these results in 1990, first just giving us something non-relativizing and then showing that IP actually corresponded to a really significant and seemingly much larger complexity class. And this was all great. It led to fantastic developments later on, the theory of probabilistically checkable proofs. But one thing that did not happen was a bunch of lower bound results using these new non-relativizing techniques. So what was going on? Well, the deities got involved with more prohibitions. If you seek a natural way to enter this complexity paradise, you must forsake the one way. And the one way they're talking about is one-way functions. And once again, they said it more clearly, namely, if one-way functions exist, you need a new, as yet undefined, but completely unnatural approach to prove lower bounds. Namely, they looked at the approaches that people had been using to prove lower bounds thus far, and they all followed well, they looked different, but they could be placed in this framework that they called a natural approach, natural proofs. And you need something entirely different unless one-way functions don't exist, which would be another form of hell. So what's relevant particularly here was that in introducing this notion of natural proofs, they also, in some sense, conceived what came to become metacomplexity. Namely, most of the time people have been thinking about computation before. They take as input bit strings that are graphs or networks or databases or something. But here, they talked about doing computation on the representation of a function just as a bit string, the truth table, this exponentially large object. And after a long gestation period, then in 2000, Cabinets and Tsai gave birth to this modern study of complexity theory by focusing on what's known as the minimum circuit size problem. Namely, your input is this bit string of length 2 to the n, which is the truth table of a function and a number s. And you just want to know if that function has got a small circuit, a circuit of size at most s. And why is it metacomplexity? Well, let's contrast this with complexity. The complexity question is to show that f is hard. The metacomplexity question is to show that it's hard to show that f is hard. And lying behind here somehow was perhaps the intuition that the reason that there had been this notable lack of progress in complexity theory for quite a while is that that task itself is computationally intractable. So the meta-complexity question in some sense is to show that MCSP is hard, show that it's hard to show that a problem, that a truth table does not have a small circuit. What do we know about MCSP? It's clearly in NP, and they showed that it's not in P if one-way functions exist. And I need to explain what I mean here, but it's provably hard to show that this problem is NP complete. That's the usual way that we try to show that something is hard in complexity theory, is we show it's NP complete or NP hard. But this problem is not NP complete under the usual notions of reducibility, Karp reducibility, polytime M reductions, unless exponential time is not equal to ZPP. Now, this is almost certainly true. So the point of this, why I'm saying it's provably hard to show it's NP complete, is that this is something people have been banging their heads against for decades, and we've been unable to show that X does not have this type of probabilistic polynomial time algorithm. And so in contrast to the many things that have been shown NP complete over the years, where the only takeaway was the problem's NP complete, here, if you could show it's NP complete, you've done something else that's very clever. The other thing that's important historically for this is that the study of MCSP, the minimum circuit size problem, harks back to the prehistory of computational complexity theory. So I hit that twice. Okay, before the beginning, back in 1959 in the Soviet Union, Yablonsky, using different terminology, published a theorem that he interpreted as meaning that the minimum circuit size problem requires exponential time. And of course, if he had done that in a way that we agree does that, then that would solve the P versus NP question. And the thing is, I mean, there's a fascinating history. You can read about it in Lance Fortnow's book, The Golden Ticket. There's a nice chapter about this. But Yablonsky had a lot of good intuitions. Focusing on this problem was good intuition, but he also historically now has been viewed as something of a villain because of the role he played in the development of mathematics in the Soviet Union, basically bringing a lot of political pressure to bear on mathematicians, and Kolmogorov was somebody who fought against this. In particular, fought against the interpretation of his result as meaning that MCSP requires exponential time. But relevant to this meta-complexity survey, the other thing that Kolmogorov did was introduce what's come to be known as Kolmogorov complexity. And Kolmogorov had been doing fantastic work in probability theory, had a great reputation, deservedly so. And so he understood as well as anybody that probability theory tells us nothing about randomness. I mean, we think of random processes. I mean, that terminology is all through Kolmogorov complexity, or is all through probability theory. But when we have a finite object and we say, well, that's random, does that even make any sense to say that something is random? And or how much information is in an object? Kolmogorov was really the first one to grasp, well, there's arguable whether or not he was the first one, because Solomonov and Chaitin were doing things around the same time, but certainly deservedly gets credit for understanding that this notion of information and randomness is really best understood through the lens of computation. And he gave this definition of the complexity of X as the length of the shortest description D, such that if you feed it into the universal Turing machine, it spits out the string X. And when a string has no short description, in other words, if the complexity is about the length of X, then that is what it means, or what he defined to mean that the string is random. So it's a great definition. It leads to a beautiful theory, but one real drawback to it is that C is not computable, which motivates the search for computable variants. And Kolmogorov certainly realized this too. Here's this beautiful quote, which is too long for me to read. Been a paper by Burman and Mayordomo, talking about the fact that already in the 60s, motivated in part by Kolmogorov's visceral reaction against Jablonski's claims, if you wanted to understand what things were really hard to compute, well, maybe looking at things like satisfiability and highly structured problems were the wrong thing. Instead, maybe we should focus on what we would call nowadays the resource-bounded Kolmogorov random strings. Now, there are different ways to define resource-bounded Kolmogorov random strings, and Kolmogorov's student Levin came up with actually a beautiful definition. This KT of X, time-bounded Kolmogorov complexity of X, is just like Kolmogorov complexity. You've got the length of the shortest description, and now you're adding a time component. And what he's adding is the log of the running time. So you want to know, looking over all descriptions, take the minimum of that sum, the length of the description plus log of the running time, such that U on D outputs X in time T. And this is in many ways a great definition, but if we're trying to relate it to circuit complexity, there's something weird that happens here, because it captures, I think, what we would agree is an odd notion of circuit size. So I'm going to have to present some definitions. We're talking about circuits of and or gates, the usual types of circuitry that we study. And let's say the size is the number of wires in the circuit, and the size of a function is just the size of the smallest circuit that computes that function. We're talking about a finite function, just a bit string of length 2 to the n. But we're going to allow oracle gates now. And this gives us a new measure for every oracle A. We're talking about size relative to A, would be the size of the smallest oracle circuit. What's an oracle gate? Well, here's a picture of one. It's just a box that's got wires feeding into it. And if these wires take on the value of some string X, this box outputs a 1 or a 0 saying, yes, X is in B, or no, it's not. Okay, so that's what an oracle gate is. This again is Levin's definition. I've told you it captures an odd type of circuit size. What is that? Let's let A be any language that's complete for exponential time, time 2 to the order n. And let's let X be a bit string encoding the complexity of a function, encoding the truth table of a function. Then KT of X is just the circuit size required to compute that function, but not on ordinary circuits, on these oracle circuits that have oracle for this exponential time hard problem. So this is the way to interpret Levin's time-bounded Kolmogorov complexity in terms of circuit size, which is actually a connection, but it's not on the types of circuits we're interested in. And in case you're wondering, why did Levin add the log of the running time? For about 50 years, we've actually known the fastest program, or a polynomial time running time program, to find satisfying assignments for formulae if one exists. And it's just to search through bit strings in an order given by their relative time-bounded Kolmogorov complexity using Levins' definition. So it's a beautiful definition and useful for a lot of different ways. But if you weren't going to add log of the running time, well, what else would you want to add? Just adding the running time would be one thing to do. But then if you're outputting a string of length n, then every string would have linear complexity, which would mean everything would be random. It wouldn't much look like a Kolmogorov complexity measure anymore. And so the obvious thing to do was to look at how to make the runtime meaningfully be much smaller. And the first way to do that is to redefine Kolmogorov's definition. This looks a lot like what Kolmogorov did, except that instead of feeding the description D into the universal machine, we're giving D and a number I and a bit B, and we're asking you, what's the ith bit of X? And if D gives enough information to figure out what each bit of X is, well, then it's a short description. And in fact, this is indistinguishable from Kolmogorov's original definition of Kolmogorov complexity. And if you play the same game with Levin's definition, then you get something that's very close to what Levin came up with. And now we just do this where we're adding length of the description plus the actual running time. And we just change the little t to a capital T, and we get a new measure. And this has the nice property that the complexity of X, the time-bounded complexity of a bit string, corresponds pretty closely to the circuit, the size of the smallest circuit computing that function. And Kolmogorov's original definition could also be viewed essentially as circuit size, but on oracle circuits where you've got an oracle for the halting problem. And we've already mentioned Levin's definition is circuit size relative to exponential time. And you can play this game for other models of computation. There's something called branching programs, which are a way, it's a circuit-like model that used to model space-bounded computation. And you can capture that with an analogous definition. Or instead of looking at the smallest circuit to compute something, you can ask about the smallest formula. And formula size can also be captured with a definition in this framework. So all of these meta-complexity problems, in some sense, are really asking about Kolmogorov complexity. What is the length of the shortest description in the appropriate formalism? And in particular, MCSP, our canonical meta-complexity problem, morally has the same complexity as computing capital KT complexity. And I say morally because as yet there is really no theorem proving that they've got the same complexity. But things you can prove for one, you can usually prove for the other, and actually frequently MKTP, which is just MCSP, where you replace circuit size with time-bounded Kolmogorov complexity, is easier to work with. But it's not the only way to play this time-bounded Kolmogorov complexity game. There's another one that I will informally refer to as K-poly that plays a huge role in the current study of meta-complexity. And because this is supposed to be a general purpose talk, I'm just going to ignore the differences. So there are important and somewhat subtle differences, but what's one beautiful result about this K-poly complexity? I titled this "The Mother of All One-Way Functions." What is it that cryptographers need to do when they're trying to design public key crypto systems or other crypto systems that maybe aren't even public key? Well, the first thing they frequently need to do is come up with a candidate one-way function. And this has been an art more than a science, because their complexity theory has had surprisingly little to say about why some of these candidate one-way functions ought to really be one-way functions. But here, in this beautiful work of Liu and Pass from just a few years ago, they showed that if there are any one-way functions at all, there's a way to build them from the problem of computing time-bounded Kolmogorov complexity in this K-poly sense. So in particular, a goal of complexity theory, or a goal of cryptographers since the 1970s, have been this hope. Frequently they've given up on this hope, but in the back of their minds, there's been this hope. Wouldn't it be great to be able to base cryptography on the mere assumption that NP is hard in the worst case? In other words, showing that NP doesn't have efficient probabilistic algorithms. So in other words, starting with the assumption NP not in BPP, NP doesn't have efficient probabilistic algorithms, you'd need to be able to conclude that this particular problem of computing time-bounded Kolmogorov complexity also is hard in the worst case. And if it's hard in the worst case, then it's also hard in average. And Raphael Pass in the boot camp gave this beautiful talk explaining this and going into much more detail on related problems. I really recommend that to you. But it's important to note that Hirahara in 2018 proved a result that looks very much like that second point. In fact, he really did show that if it's hard in the worst case, then it's hard on average, but using a somewhat different notion of average case complexity. And so I entitled this Pass and Hirahara, Destroyers of Worlds. What worlds am I talking about? And Pagliasso has this lovely paper where he describes possible worlds in which we might be living. And the two that are relevant for us here are Pesiland, where there are problems in NP that are hard on average, but in spite of that, we still don't have any one-way functions. We don't have any cryptography. So that's a particular form of hell. And then this other world we might live in, heuristica, might seem like a pretty good place to live, because every problem, even if NP is different from P, and so things are hard in the worst case, everything is easy on average for any kind of distribution that might arise in practice. All these problems are easy. And having things be easy sounds good, except that if you would like to have cryptography, if you want to have secure communication, then this is another form of hell. And so I've shown these worlds exploding because the work of Pass and Hirahara in different papers, and here in this Hyundo deity, we see a long line of other faces. You can think of them as their co-authors that I didn't have room to build their pictures for. Basically showing that these worlds are unlikely to exist. Now, the destruction is not yet complete, but honestly, we've come much further in this direction than seemed plausible just a few short years ago. And it's looking more and more likely that one might actually soon be able to show that one or the other or both of these worlds can be ruled out. And this is just a sample of lovely work that's been done on relating worst case and average case using the tools of MetaComplexity. So let me paraphrase a nice result of Hirahara's from 2020. The polynomial hierarchy is this class of problems sitting right above NP. And in fact, if P is equal to NP, then this whole hierarchy collapses to P. And there's something that's hard on average in that hierarchy if and only if this particular problem, the problem of computing time-bounded Kolmogorov complexity with an oracle from the polynomial hierarchy, is hard in the worst case. So this is a particularly quotable, crisp result showing that a version of heuristica doesn't happen. In other words, something is hard in the worst case if and only if things are hard on average. And like I say, this is just a sample. There's a lot more that's been done in this direction, but there's other ground I wanted to cover. Metalogic and metacomplexity. One big theme of the semester explores how metacomplexity provides new insight into the field of proof complexity. In other words, lower bounds on the length required to prove that a formula is a tautology. But Rahul Santanam will be giving a talk later in the semester for the Karp Distinguished Lecture Series, and he will talk on that. So that's just a forward pointer. So Rahul and I have, I think, only one paper together, and the title of that uses this phrase, pathetic lower bounds. What are we talking about there? In complexity theory, we want to separate complexity classes, which means we want to prove superpolynomial lower bounds. But our current best efforts fall far short of this. For circuits, we have really nothing superlinear, which I think is pathetic by, it's hard work that's been done to get us as far as we've come, but still, it's a pretty sad state of affairs. De Morgan formulas are just logical formulae that you can build with and OR gates and OR operators. And they're the best lower bounds we have for something in NP is approximately cubic. And for branching programs, this other model of computation I mentioned, the best lower bounds we have are approximately quadratic. And part of the art of proving lower bounds is just finding a problem that's suitable for proving lower bounds. And the original cubic or quadratic bounds that people came up with, were for problems that were specifically tailored to the task. Let's show that this is a hard problem. It turns out that MCSP is sort of a general purpose hard problem in the sense that the lower bounds for MCSP on these and some other models essentially match the best that are known for any explicit problem. And there's this nice paper by Geraci, Cabinets, Liu, and Mariziotis that proves that. And this is related to, the whole reason to introduce this notion of pathetic lower bounds is this program that arose in the study of metacomplexity for something called magnification, where you take a pathetic lower bound and you use machinery to try to blow that up into something that turns into a really impressive lower bound. And in order to give a crisp example of that, let's look at a parameterized version of MCSP where I'm fixing the second part to be some particular size S, and MCSP S is just a set of those truth tables that have functions that have circuits of size at most S. Here's a pathetic lower bound. Geraci, Hirahara, Mariziotis, and Yoshida proved that for S equal n to the epsilon, MCSP n to the epsilon is not, requires essentially quadratic time on a model of computation that we don't really care much about. namely probabilistic one-tape Turing machines. How many people have actually programmed one-tape Turing machines? Okay, this is a room full of complexity theoreticians, and fewer than half of you raised your hands. And there's a reason for that, is because it takes a certain amount of courage to say that it's a meaningful model of computation. I mean, Hartmanis and Stearns deserve a lot of credit for going out on that limb and saying, you know, let's use this model. And then they went to the multi-tape machine, but still, one-tape Turing machines. Okay, you can prove a nearly quadratic bound. Why should anybody care? Well, here's another result by McKay, Murray, and Williams. If this thing that looks like the same problem, MCSP with the size parameter n to the b, if it requires more than time just over linear n to the 1.01 on a one-tape deterministic machine, then p is not equal to np. Now, let me quote Elon Musk, let this sink in. We know that it's hard on a powerful model of computation, probabilistic one-tape Turing machines. And if it requires anywhere near that much time on a one-tape, even deterministic Turing machine, then you've won $1 million. You've separated P from NP. Well, okay, it's not really the same problem because epsilon and beta aren't the same number here, but still, this shows that there's something pretty impressive that can happen with magnification. You take something that looks like a completely uninteresting lower bound, and you can get something really magical out of it. And some of these lower bounds are things that seem like they ought to be provable. And that's the general theme of magnification, taking modest sounding lower bounds, and you can have huge consequences. Let's give another example. Recall, MCSP requires nearly cubic size De Morgan formulas. And this holds also for MKTP because it's kind of the same problem as MCSP, as well as for Levins' notion of time-bounded Kolmogorov complexity, because, you know, unsurprisingly, because this is, you know, that's up there, and it's exponential time hard in a particular sense. So here's a theorem by Oliveira, Pish, and Santanam. If this problem requires just slightly more than cubic size on formula size, well, then you get a lovely circuit lower bound. Now, if you're not working in complexity theory, showing that exponential time requires more than logarithmic depth might seem like another example of a pathetic lower bound. But trust me, this would be a very exciting lower bound. We don't know how to prove anything close to that, you know, even for non-deterministic exponential time. So what's your reaction likely to be? Well, you're thinking that means you just can't prove circuit lower bounds that are, you know, formula size lower bounds that are more than cubic. We don't have any examples of things like that. So so maybe this doesn't seem like a very plausible path to prove exp not contained in NC1, but let's give another example. This is the problem of computing Levins complexity, again, for this fixed size n to the epsilon. And if this requires size slightly superlinear, n to the 1.1, on this model that's just formulas where you've got parity gates at the leaves, then again, you can conclude exponential time is not NC in NC1. But the amazing thing here is that this lovely paper of Tal does give examples of pretty easy problems that require nearly quadratic size on that model. So again, this is even more a more compelling example maybe of a way that these meta-complexity lower bounds combined with hardness magnification might lead us to new separations of complexity classes. And if you want to know more about this, there's a nice paper by Chen, Hirahara, Oliveira, Pish, Rajgopal, and Santanam that explains more about what can be done with magnification, as well as some barriers to possible progress on that front. So let me shift gears a little bit and go back to something I said earlier about MCSP and the reasons we don't know it's NP-complete. And let me focus on that. I just put a circle around there. It's not hard for RP under Karp reductions, unless X was equal to ZPP. And the way to get around this is maybe to consider more powerful notions of reducibility, randomized reductions. So a BPP-M reduction is just given by a deterministic polynomial time computable function f, such that if you have a yes instance of A, then for most random bits, f of xr gives you an instance of B, and x not in A says that for most random bits, when you plug that in, you get something that's not in B. So it's the usual notion of M reduction, except for probabilistic generalizations. And a lot of close relatives of MCSB have been shown to be NP-complete under these randomized reductions, including some pretty natural examples. A lot of the functions we want to compute don't have a single bit of output. They've got lots of bits of output. So multi-output MCSP was shown by Ilongo, Loff, and Oliveira to be NP-complete under these reductions. Conditional KT complexity, so the complexity of X given Y as an additional input, is building on a lovely result of Ilongo's. You can show that this problem is also NP-complete. And a very impressive result recently, Hirahara showed this problem MCSP star is also NP-complete. What's this? This is just like MCSP. You've got the string of length 2 to the n. Some of the input, some of the positions are ones and some of them are zeros. And then you've got these don't care positions that are stars. And with a technical tour de force, he showed that this problem is also NP-complete under these probabilistic reductions. And there's actually much more that he did in that paper. And with all of this progress, it's reasonable to ask if MCSP can be far behind, or if it will be added to that list soon. Shifting gears yet again, but still talking about probabilistic reductions. I mentioned interactive proofs. Interactive proofs, as soon as they were introduced, gave rise to this notion of zero knowledge proofs, which is a way that a prover can convince a verifier of some fact without revealing any other information except that single bit. I know this secret. And this has had very important and widespread influence in the theory of cryptography. And it gives rise to this class statistical zero knowledge that is probably in NP intersect co-NP, but it's not even known to be in NP. And there is a non-interactive version of this that's also been studied because of applications to cryptography, where it's an interactive proof where the verifier and the prover can see an input and share some random bits. The prover speaks to the verifier, and then there's no more interaction. So it's a proof that the verifier can work with just with the available shared randomness. Why am I mentioning these classes? First of all, let me mention that this subclass has got something hard in it if and only if SZK has something hard in it. So in some sense, this class NISZK, N-I-S-Z-K, contains all the computational difficulty of statistical zero knowledge problems. We're going to relate that to the canonical metacomplexity problem of computing Kolmogorov complexity. And here we're not talking about time-bounded Kolmogorov complexity. We're talking about a completely non-computable notion of complexity, where we've got yes and no instances. The yes instances are the random strings where, let's say, X has got no description of length less than half the length of the string. And the no instances are where there is a description, so they're very non-random, that's significantly shorter, where significantly is by this sort of approximation error term, where that term for these results can be anything super logarithmic and subpolynomial. So anything where the complexity is too close to the length of X over 2 is just a don't care instance. Why are we introducing this? Oh, I should mention that for people who are real complexity experts, there's different flavors of non-computable Kolmogorov complexity, and these results hold for all the favorite versions. Recent result: if A is any decidable promise problem, in other words, the yes and no instances are decidable at all, then that problem is in this non-interactive statistical zero knowledge class, if and only if it's randomly reducible to this non-computable problem of approximating Kolmogorov complexity. And I'm simplifying a little bit here. There's an honesty requirement that I won't bother to define. But what's striking about this is that this is the first time that a really well-studied and familiar complexity class has been characterized in terms of efficient reducibility to something that's not even decidable. And in fact, it's an important metacomplexity problem, this Kolmogorov complexity problem. And there's a related suite of theorems about a space-bounded version of non-interactive statistical zero knowledge, where the reductions, instead of being probabilistic polynomial time or probabilistic log space, or even probabilistic NC0. Everybody in this room knows about NC0, but for the wider audience, these are just circuits with every output bit just depends on a constant number of input bits. So there's hardly any computation happening there. So why do we care about these NC0 reductions or this log space class? Well, the reason it was originally defined is that a lot of the problems in NISZK that people do care about are in the log space class. But the reason I care about it is because we get results about reducibility under projections. And I'm going to define projections in just a bit. But anything that's in this funny NISZK L class is reducible to this non-decidable problem of approximating Kolmogorov complexity via a projection. And it's also projection reducible to the KT random strings. So what are projections? This little trapezoid here represents a circuit, and I'm putting the input at the top and the output below. So we're thinking of just pouring the input at the top and getting the output out at the bottom. And the reason we can think about pouring it is that these circuits, if they're projections, have no gates. It's just wires, or if you like to think about it as plumbing. So you've got these pipes. At the input level, you've got every input bit and its negation. And then you've got these little pipes or strainers running through here. And at the bottom, you've got a template of some bits that are just constant, and other bits, you can duplicate bits. I guess I didn't mention that here. But every other position here that's not a constant is just connected via a wire or a little tube to something at the input level. So there's really no computation happening in these projections. It's just like a strainer. So why do we care? Remember this problem, I mentioned the strings that are random with this KT notion of complexity. Well, that's easy to see as in NP. And this space-bounded class contains a reasonable subchunk of polynomial time. In particular, it contains non-deterministic log space as well as some bigger classes. So putting this all together, if NP collapses to NL, then there's a projection that if you feed in a bunch of zeros, spits out something with high complexity. But if you just flip a whole bunch of coins and have something with a ton of information, it's got low complexity. So in other words, under this unlikely condition that NP is equal to NL, you get this transmutation where you feed hardly any information in at the top and you get high information out the bottom. And if you feed a bunch of information in at the top, somehow it evaporates and you get no information at the bottom. So that seems crazy. It seems like there's no way that ought to happen. And it even, since we're talking about basically an information theoretic object, it seems, and we're kind of factoring computation out of this as much as possible, it almost seems like you might even be able to prove that that's possible. And if you could do that, well, then you've separated some important complexity classes. So my time is nearly up. There's a lot more I could have talked about. There's been a lot of developments I didn't mention, including connections to machine learning and probabilistic Kolmogorov complexity. Here's a classic picture of paradise. I started off by saying that there was optimism, maybe that MetaComplexity will help us answer the long-standing open questions in complexity theory. Is that really true? Well, I don't want to lie. Actually, I'd love to lie, but maybe there's a little optimism. At least it's true that recent work in complexity and metacomplexity has already overcome a lot of apparent barriers to proving important results, and consequently we know a lot more than we used to. And at the very least, complexity theory has given us some new angles to investigate in approaching some of these long-standing questions. And I'm definitely optimistic that further developments in the field will bring us further along the road to enter this paradise of complexity. And I have come to the end. Yes.
For your final, this crazy transmutation thing. So the way you would produce information by passing zeros is because projection can negate variables. Is that how you get?
Well, it's a non-uniform object. So you could easily prove that there's no computable function that can do this. But for each input length, it's conceivable that there could be this little strainer, this little piece of hardware that magically can do that. I just don't see how. And I would love for somebody to show that it can't possibly exist.
Yeah, and I guess my question was even more, so even for a particular length, the strainer can negate variables. I guess that's.
Well, you've got the negated variables provided at the input level.
Because you said f of all zeros is.
F of all zeros. So what would that, this would be 0, 1, 0, 1, 0, 1. But in fact, you can get a lot of complexity just by hardwiring in some of these bits here at the output level. And that, in fact, will have to happen. You can show that. But you can't hardwire too much information in because you got to drop below that threshold. So there have to be something really weird happening.
Is the condition that for every high complexity string you get low complexity?
Yes, for every high complexity string, you get low complexity.
Difficulty is between the problem, the gap between the process is just too small. Right there.
Well, I mean, yeah, in the paper that presents this, we do show that you can't do this if you want the string here at the output level in the high complexity setting to have complexity at least 4/5 of the length, and in the low complexity setting to have 1/5 of the length. I think that 1/5 to 4/5 gap is certainly not optimal. You should be able to improve that. If you can prove it all the way to half plus 2 to the square root log n and half minus 2 to the square root log n, well, then you've got a really nice theorem. Yes.
Do you think there might be, on the contrary, a barrier to these kind of results, MetaComplexity?
Barriers turn up every place we look. I haven't figured out why there would be a barrier to this particular approach yet, but the longer we stare at it, we'll probably discover that there's, like I say, I'm not entirely optimistic that this will work. I'm just not completely convinced it won't. Which is something.
Can you put more methods?
Of course. In fact, there's a nice paper by Rahul, and I forget who your co-author was. I think Han Lim, right? Rahul and Han Lim basically looked at the sort of a meta operator to prove something concrete about problems we care about. So the short answer is yes, although if you just define it without having a good reason, it might not be very interesting, but sometimes you can get something interesting.
Thank you.
Please, out in the